evaluate the thrust torque for the given data at the operating condition, steady state values, both starting and final, and compare with your experimental data the change in values, because the absolute values, I find that there are some differences and I want to know what is the reason. You think about it, give the reasons. Why, what? Okay? This is clear. 900, 1300. Okay? I have given the blade data and geometry data, everything is there. Pitch angle. Calculate thrust torque with what model you want to use, that you use it. What inflow model you will use, etc. And then see what is the difference between this and how much the theoretical difference compared to the experimental difference. Because experiment also RPM jumped from one value to another value. As a result, thrust jumped, steady state torque jumped. This is one set of calculations. Okay. In the second one is the time variation. Okay. You write your own model, theoretical model. I am not saying you should match with this. Theoretical model, you formulate how time variation will be modeled. Okay. And show that your equations predict a similar trend. That's it. Is it clear? So one is for steady state, another one for time variation. These are the two. And this is going to be, I will evaluate it as an example.
So we'll submit the assignment and...
You submit the assignment, that's all. What else?
It's not like we have to sit for an hour and, but how can we sit?
No. There's nothing like sit for an hour. You have to submit it on that day, whatever date I specified. Because I made, see, I will tell you what are there are still some questions.
Yes.
Because the load cell gives only the change. Because steady state, there is nothing like, if you keep a weight, the output of that will keep on drifting. So you will have 1 volt at this time, then after 20 seconds, you will find the output voltage will be different for the same weight. Okay, so you will not be able to see that what happened, the weight has changed or something. Whereas whenever there is a jump, the jump is correct. So that is why I said calculate for steady state values, take the difference. The difference how much compares with the experimental data. Whatever you get, that is the result. Because then you give the reason. I want you to think and then give your own reasons. What could be the likelihood for this difference, if there is a difference. Okay. And the other part is the time response. Okay. Now, with that I have given you the sheet which is the expression for the thrust, side force, longitudinal force, torque, and also the moment. Okay?
Yeah. The time response need not correspond to the experiment.
No, time response, but you can take the data.
Even in steady state values?
You say what changes, because some initial value to final value. That's all. How it changes. That is enough. Okay? But you can take this data is same, but then you will find out how it varies. Because time response is much more complicated. Okay? Now,
sir, I didn't understand if you have to derive purely from theory a time.
Yes, theory.
Or do we try to match it with
No matching of experiment. Theory. Okay? That is from theory. I want the theoretical equations, formulation of the equations which describe the physics of time variation. Okay? Not curve fitting. Please understand. Is it clear?
Yes.
Okay. Now I have given you the sheet containing the mean thrust coefficient, force coefficient, etc. And there are two additional terms which I have added, pitching moment and force moment. That we will cover as we go along the lecture, because I have introduced some new terms. See, in all these loads, we had theta 0, theta 1c, theta 1s, and then we had beta naught, beta 1s. Of course, sigma solidity ratio is there, lift up slope is there, everything is there. But these 6 quantities are given in the loads expression. Now, you have to know how do I get the flap response for a given flight condition with an input of pitch angle. Okay? So for that we need flap equation. So that is why now I am going to say rotor flapping model, or you may call it flap dynamics. Okay. Only flap motion. That means we are going to derive the equation of motion for the flapping of the blade. But before you go and derive, we have to make a idealization. What type of idealization you will have? Okay. Because you know that the blade is attached to the hub. It can be with a hinge, and it need not be with the hinge because it can be bolted. That is a hingeless blade. So what we will do is we will have a hierarchy of models. The very first one is you put this is the blade. This is called centrally hinged. Rigid blade. And this is rotating about this. Centrally hinged is, this is the hub center, like a pendulum. Because it is pendulum, you hold it in some place and it just oscillates. Same way, the hinge point is here. This is one type of model. This is actually easy first to write the equations. Subsequently we will, because this is the very, very crude model. Of course, teetering rotor. Teetering means where the hinge is right at the center. This model is valid, but only thing is this is attached to the other blade. So when one blade goes up, the other blade goes down. Okay. So that is why that you have to derive separately. Here we are taking one blade only. Then the slightly more, I would say, complicated, that is also centrally hinged, but this is also centrally hinged, spring restrained, rigid blade model. Okay. Okay. And here, see, this is a hinge but I have replaced the hinge. Hinge is still there, but I put a spring. It is possible they put some elastomers in certain blades. And what is the effect of that, that you will see later. As we go along, but slightly more advanced model is, you can take this is a articulated blade. That means offset hinged, okay? Offset hinged rigid blade, okay? And then the final model is this. You put a spring also. This is offset hinge there. Okay. Spring restraint. Rigid blade model. Always I say rigid blade, okay? Because the blade is rigid. In real life, the blade is not rigid, it is flexible. But then it is rotating. So how do we really match these models? What happens is the flexible blade usually have more number of vibratory modes. Okay. The first mode, because if you have done vibration continuous systems, I presume that you have done that. The natural frequency of a continuous system, you have infinite number of natural frequencies. You are looking at the fundamental frequency. And then the fundamental of whether it is a hinge blade, articulated blade will be like this. They all you try to match. So this model, all this, represent only first frequency of the blade in flap. It's an idealization. Okay? And this is good enough for most of the preliminary calculation. As a matter of fact, some of the industrial codes use only this. Because today, of course, people have added more things. But for earlier days, what was developed in the 60s, they were all using spring restraint, offset hinge, rigid blade. Because that gives the physics here. Of course, it has its own limitations, but which is good as a model. Now, we have to derive the equation of motion for the blade flapping as it goes around the azimuth. Okay? So, blade dynamics. First we will take this and then we will add this. Later we will come to these two. Okay? Because I would like to proceed in a systematic manner. I will first write this, then we will go further, because each one has certain interesting characteristics. So that you will slowly understand, oh, this is what it really means when you do a blade analysis. Because please understand, we are talking only about the flap motion. Similarly, you can have lead lag motion and then torsional motion. And then all of them can be coupled. Okay? But we will restrict ourselves to first this type of model. Write down the equation of motion. So how do we write the equation of motion for this? We have the basic dynamics, and of course aerodynamics is there. You have to combine both. The external loading is aerodynamic, and because it is moving, you have a inertia. Okay, and there is no restraint here, so the moment must be balance. So the equation, first you write inertia mi plus m external, which is actually aerodynamics. This is 0. For this model, please understand, that is for this model. Okay. Whereas when you put a spring, you will get a spring force also. Okay. So that you have to add here. Here there is no root spring. It is a free, like a pendulum. It's free to. Only thing is you have to model it properly. This is rotating. You have to take the centrifugal load into account. And we make, when we derive, we make lot of approximations. That's why what I felt was first I derive for this. Make all the approximations, then you will know that this is what is being done. And finally, I will just directly use the same equation, add the spring. Okay? When I add the spring, I will get the next. Of course, these two models are slightly different because you have an offset. Okay? And offset will come into the equation. That part we will do later. Alright? Now we will take the equation of how do you develop the equation, because this is basically dynamics of a rotating beam. Okay, so we'll go very systematically. So this is my omega, and please understand, now this is in the rotating frame. So this is my Ix, and if you take any section, this is like a beam, that's all, a line. We have ideally like a line. You will have an external, which is the aerodynamic load. This is at a distance r. Okay. So the position vector of this Rp, position vector, of any arbitrary point, arbitrary section. Actually, this is because this is K and this is my J axis. Okay, the rotation is about the J axis. J, this is K. Flap motion. Flap is alone. That is a rotor RPM. Okay. This is capital omega is about K. Flap motion is about J. So now you know the position vector, you can find out the velocity. Velocity is r dot plus omega cross r. Okay. Because this is a rotating coordinate system. Alright. So this will become r dot will be minus r sine beta dot I plus r cosine beta dot k plus omega is omega k cross your r cosine beta I plus r sine beta k. So you know k cross I is j, so that other term will drop out. So you will have, this can be replaced as plus omega r cosine beta j. Okay. This is my velocity. Then I go and get my acceleration, okay, of the same point. Acceleration is, if you want directly acceleration, because if you know, see, when I say acceleration, it is an absolute acceleration of a mass point which is attached to the, which is in the blade, which is rotating. You can directly use that expression. Okay, acceleration will have, you have the relative acceleration, you have the Coriolis acceleration, you will have the centripetal acceleration, you will have the angular acceleration. So you will have 4 terms, alright? And then if your hub is moving, that acceleration also will come, alright? So that is how you have to develop the acceleration of any point. Here I am directly writing every step I am going through, okay, because this particular term comes because you differentiated this term, r is constant, because the position vector, this distance is fixed, okay. Beta is varying, I, that is also changing. So you will have di over dt, and k is not changing, okay. So di over dt becomes actually omega cross this term. That is how, because in the rotating coordinate system, the factor omega is actually the angular velocity with which the coordinate system is rotating, okay. Because this is basic dynamics. I hope you have studied some couple of years back. You don't forget it, because dynamics is very, very important. Because I cannot go and then start teaching that part. Okay, you take it as though this come, you go back and read, brush up your fundamentals in deriving the equation. Now you write the acceleration. Acceleration will be derivative of each one of them plus again omega cross, because I dot, k dot is 0, j dot also will be there. So omega cross, this expression again it will come, okay. That's why I will write that acceleration is, first take this derivative, that will be minus r cosine beta dot square, okay, I. Then you will have another term, minus r sine beta double dot, okay. So maybe I put that I outside. Then j term plus omega r, sorry, with a minus sign, sine beta dot j plus minus r sine beta dot square plus r cosine beta double dot k, okay, plus you have the, because of the rotation, you will have omega cross this expression, the v, okay, omega cross v. Now when you, and I would say when you add those things, I erase this part, okay, your acceleration expression will be minus r cosine beta square r sine beta double dot, and then minus, we'll have 1 minute. What is that term? omega square r cosine beta I. Okay. Then plus we will have omega r sine, sorry, with a minus sign, sine beta, beta dot, omega r sine beta, beta dot. This is j. Then plus minus sine beta, beta dot square plus r cosine beta, beta double dot. Okay. So this is my full acceleration expression. Okay. You will find that now I will erase this part. Okay. How do we get there? Inertia force. Inertia force is basically you take the negative of the mass times the acceleration. Okay, that is inertia force. So you will get inertia force is minus mass of this element, I call it dm. That is the elemental mass. This is my inertia force. Okay, into that entire expression, acceleration. Now I have to get the moment, because my equation about this point all the moments are zero, because there is a fixed point. Okay, external moment, inertia moment, everything is zero. If you want to write in terms of Newton's second law, you can get external moment is equal to mass times the angular acceleration. That part you can write it, but otherwise what normally we follow is, because if you have a very complicated motion, write the complete acceleration expression, take the inertia moment, force, and then take the moment, then you will get external moment, inertia moment. You add both of them. If you don't have a spring, it is zero. If you have a spring, add the load to the spring also. Okay. So here your mi, inertia moment, about the root, that is about O. This is 0 to r. You have to take this is the inertia force acting at this point. So if you want to get the moment, it is r cross f. So your r is r cosine beta I plus r sine beta k cross minus dm a. Alright, dm you can write it as, you can write rho dr. You can write rho is the mass per unit length, dr is the elemental length. Okay, that means what you have taken this cross product. So you substitute all the things, take the entire cross. Okay, and that cross product will give you this. Maybe I erase this part. Okay. You will have mi is rho 0 to capital R cosine beta to omega r sine beta beta dot k plus minus r sine beta beta dot square plus r cos beta beta double dot j. Because this algebra you please check it out. Okay. Plus r sine beta r sine beta, beta double dot plus omega square r beta, beta dot I dr. Okay. This is the full expression. You have all I, j, k, all components are there.
So right, why is it minus dma?
See, because I am adding, see, F equals ma, right?
Yeah.
I am taking the ma to the left side. So external force plus inertia force is 0. It's basically dl number. That is why external movement, I am taking it as external movement plus
Yes.
inertia movement is 0. Okay. Now this is my full expression. You find I have, if you simplify, okay, but I need the equation of motion only about the j axis, because even though I may have moment about the k axis, alright, or I don't take that into account, because I am writing the equation only for out of plane motion. Even though inertia, you will have other moments coming in, please understand, because you will have other terms come into picture. But we basically say, if you are writing the full equation, flap, lag, torsion, then you take every term. Okay. Right now, in our formulation, we are considering only the motion about the j-axis, but the j-axis, please note, it is also changing. Okay, it is not fixed. J-axis is changing. I am calculating what is the moment about the j-axis, because that is the one which goes to flapping. Okay. So the moment about j-axis, if I look at it, the component of j is one term is here and here another term. Okay. If you add both, that is about j-axis. Mi, because mi is a vector, now I am taking it only about the j. You will have 0 to r cos beta minus r sin beta, beta dot square. Here you have r sin beta, r cos beta, beta. So they will cancel out. This term will go out. Okay. Then here you have r cosine square beta double dot. Here you have r sin square beta double dot. Okay. Sorry, r square sin square. So you will have sin square cos square 1. So you will have r square beta double dot. And then you will have this term plus omega square r sin beta cosine beta dr. Okay. Which you can now write it as, okay, density I have taken it out, either it can be inside or outside, it doesn't matter, we can put it inside also, because if the mass is varying along the blade. Rho dr is the mass per unit length into r square, that is basically mass moment of inertia about the point. I will call it I B beta double dot. Oh, here also one r square is there, right? Plus omega square sin beta cosine beta. here the double dot, there are derivative with respect to time. This I am approximating now when my angle is small. Cosine beta is 1, sin beta is beta. So I will write this as IB beta double dot plus omega square beta. That's all. So my inertia movement in the flat direction about the j-axis is this. Now you see there is an acceleration term, and this term omega square is due to centrifugal force. Okay, that is the centrifugal stiffness, because you know when you are looking at an equation, later, now it is only an expression. When we get the equation, you all know mx double dot plus kx equals some external force. Okay, this will be in the similar form. Okay, and you find this particular term is due to rotor RPM. That is the, you call it centrifugal stiffening, because if the omega is 0, then that term is not there. Then the blade will simply come down like this. Okay. Now you look at the external force. External load is only the aerodynamic load. We will write that. That is a fairly simple expression, because your aerodynamic load is again you can take 0, capital R. This will be, because this is the Fg. We are taking lift force, because the drag force is along this direction, and the drag is not going to give any contribution to flap moment. Okay, so we neglect that, we take only the lift force. When you take lift, lift is Fg into R. Okay, so you will have R cross, so I will write R cosine beta I plus R sin beta K cross your force. Force is, you will have minus Fg sin beta I plus Fg cosine beta K dr, because this force is along. So I take a component like this and like this. Okay. Now you can take I cross I is 0, I cross K is J, and similarly I cross, okay, that is minus J, this is K cross I is J. So this movement will be only along the J axis with minus, because this is cosine square, this is sine square. Okay, you will have 1, you will get minus R F G dr. Okay. That's all. Now your flap equation is clear. I'll write the flap equation. Yeah. No, this is along J, only J. J is the only moment, only one component along the J. So I am just taking moment. Now I add both inertia and aerodynamics and write my flap equation, which is flap equation. This is IB beta double dot omega square beta plus Fg dr dV. This is my equation. Now you have to go back and substitute what is Fg. Okay. Because Fg is nothing but our lift, and we wrote, I will write Fg expression just for, you look back your notes. half rho A C omega. This is in mu sin psi whole square theta minus lambda plus r over r beta dot plus beta mu sin psi into r over r plus mu sin. Okay. Now what I am going to do is, here these dots are derivative with respect to time. Here I have written this dot also. This is derivative with respect to psi. Please understand. This is non-dimensional, whereas this is dimensional. So we will replace this also. We will put it d over dt. We can put it as omega d over d omega t. This we call it as omega dot. So that means this term, if I non-dimensionalize, that will be omega square coming out. Okay. So I can write that part and then put all the equations in non-dimensional expression, because you know that this is already r over r everything. So when I put this d r over r, I will put a capital R, make it 0 to 1, and here also I will put a r over r. That means I will have a r square getting multiplied. Okay. This is just a non-dimensionalized in the whole equation. I erase this part. I will write the non-dimensional equation, then we start discussing the whole thing. You will have IB omega square beta double dot. Please understand here that is non-dimensional time derivative. That is d by d omega t. Okay, this term. That's why I have taken a, and here you have beta. Equals, I will take half rho A C omega r whole square r square 0 to 1 r bar, where r bar is r over capital R. Okay. R bar into r bar plus mu sin psi square theta plus lambda, sorry, not plus, minus lambda plus r bar beta dot. This dot is as it is because this is a non-dimensional time, that dot, plus beta mu sin psi multiplied by r bar plus mu sin psi close b. Okay. This is my full class equation. Now you find within this is an integral over dr bar, sorry, dr bar. So I can actually multiply everything because mu psi beta dot lambda, assuming lambda is constant over the span. Then I can integrate the entire thing for r bar separately. Write the moment equation in a relatively simpler form. Okay. And even theta is, please note, this is the theta what pilot gives. That is theta I. You can have a, if you have a twist built in that, then twist will come here. Okay, that will have a theta twist R bar. Okay, that term also will come here. Okay. Now if you write, assume uniform inflow, okay, inflow, then and theta equals theta I plus R bar theta twist. If we assume that linear twist, put it back here, integrate, okay, you will get your equation like this. But finally I am going to write it in this form, which is a relatively simpler. This is theta double dot plus beta equals, okay. Now you see, I take this IB omega square, divide here. Okay. When I do that, rho AC, one of the omega square will go up, and then R power 4 over IB. So I will have rho AC R4 IB, and I am putting some M flap. Okay. Just I will write this expression. What is MF? MF is, it consists of several terms. Okay. You will have M theta theta I, M theta twist plus M lambda lambda, M beta dot plus M beta beta. Okay. Please understand, MF has theta I, theta twist, lambda I am taking it as a constant, beta. Okay. Now each one of the terms I am just writing it, and that completes my flap equation, and I am going to call this number, okay, this is a non-dimensional number, okay, this is Locke number, and the symbol is gamma. That is, this is the aerodynamics, because rho A is the lift curve slope, density of air. So this is aerodynamics, this is inertia. So this term Locke number represents the ratio of aerodynamics force to inertia force of the blade. Now let me write M theta. You can actually write NF itself. You can write theta I 1 over 8 plus, I will show later, please note that now, plus theta twist 1 over 10 plus mu over 4 mu square over 6 sine square psi minus lambda 1 over 6 plus mu over 4 sine psi minus beta dot 1 over 8 plus mu over 6 sine psi minus beta mu cosine psi bracket 1 over 6 plus mu over 4 sine psi. Okay, this is my full equation. So now I will go and then show. You don't have to worry, I will give you the equation. This is the model. Whatever I have derived, I am just showing it. Because I will get back to the final equation. Then we will start discussing the equation. We have the, because uniform blade, because I integrate equation of motion, moment balance about the root, and I get inertia effect, external aerodynamic. No hub moment. I am not putting another spring here. If I put a spring, I will add that term here. That part will come later. Okay? Now, when I get the full equation, the equation is this. This is what I have written there. Beta double dot plus beta is gamma MF. Gamma is the Lock number. And MF is given here. Okay? Please note MF is this. Now, if you look at this equation, we will theta I, what I use as theta, it is actually theta I. Theta I is given by, this is what the pilot gives. Theta naught, 1 is sine psi cos psi. That is the input pilot is giving. So you have to multiply that term here. Theta naught, theta 1 c cos psi, theta 1 s psi, everything will come in this place. Input. These two terms, there is a dot, beta dot, which is actually like a first derivative of flap motion, it's like a damping term. And there is another term which is beta, cosine psi. That means this is a spring term. But the spring term associated with the forward speed, mu. Okay? Now if you take these two terms to the left hand side, you will have an inertia, you will have a dot, time derivative term, and you will have a spring term. And then rest of the quantities are directly input and twist. Blade twist, if it is there, otherwise it is 0, 0, and your inflow, whatever constant if you have, that is the constant you can have. Now you are having the flap equation with coefficients which are of sine, okay, let me, okay, it's all right, with the sine psi, cosine psi, within the coefficients of beta dot and beta. You follow? Because beta dot at a sine psi. Here beta mu cos psi 1 over 6 and then another mu over sine psi. So this will be going mu square over 4, etc. That means your spring and damper. Whatever damper means, there is not a damper, it is actually a derivative term, damping term. They are functions of psi. And psi is your independent variable. Derivative is with respect to psi. So your coefficients, please understand, left side is purely inertia. I am getting the damping term coming from aerodynamics. Please understand. In the flap motion, the damping comes from aerodynamics. So have a spring term, which is a little, it's like an aerodynamic spring. Okay? When you put everything on one side, your equation will be beta double dot. Maybe I write that, then you will be able to see clearly how it looks. Because you can take this beta double dot plus beta dot term is here. Beta dot 1 over 8 plus mu over 6 sine psi plus beta 1 is already there, plus you will have mu cosine psi over 6. right, plus mu square cosine psi over 4 equals rest of the terms, that is gamma times m theta theta I plus m theta twist and plus m lambda. Okay, this is what your equation. Now you are having a time varying equation. This is a parametric excitation type of problem. Yeah, you have a gamma and gamma here and gamma there. Okay. Now what is that we are looking for? The solution. Because the solution is, we said lambda is a constant. We have to substitute for theta I. Okay. So I erase this part. I have to substitute theta I is theta naught 1c times psi plus theta 1s times psi. I have to substitute this. Then essentially I need to know what is the solution. Please understand, lambda is, assuming lambda is, I have to get these quantities. So I am assuming okay, only first harmonic, I am not considering other harmonics. That means assume, this is my solution, assume. Okay. That means what you do, you have this equation, substitute this down on the left hand side, substitute this on the right hand side and collect all the constant terms, sine psi terms, cosine psi terms, and then you will have 3 equations, and those 3 equations you will get, they will be algebraic equations because all the derivatives are gone. Algebraic equations, from there you can get a relation between this to lambda and theta twist. And of course mu is always there because everywhere mu is sitting there. Okay. Now this is called the harmonic balancing because you are looking for steady state response. Steady state means these are fixed angles. There is no change. How, as the blade goes round and round, what will be its harmonics of flap motion? It's like a steady state solution. Okay, there is no, it is only the particular, there is no transient part. Transient part is 0 there. But if you take this, I am not going to write the procedure. Okay. I am only saying you take this, substitute here. There are 2 ways of doing the problem. One is called you substitute, collect all the terms, put them together. This is an algebra. Another one is an operator form. Operator form is you integrate that equation first and then again multiply by sine psi and then again multiply by cosine psi. Like that. That is like a Fourier coefficient. How do you get? Same way. Okay, that is an operator form. Another form is put this harmonic balance. Okay, this is another technique. Now, this is the algebra which I will not be doing it. I am only directly writing the final answer. Okay. The final answer is this, which I will give you. The final answer is you will get 3 equations. Alright, we will just only discuss now. But no, don't have to take it because this I decided it as You cannot keep on writing everything. Now onward you find that it becomes messier, too many things. You have three equations. This is the constant term part. And actually this is the sine and cosine. Sine, cosine are one of them. Okay? You have to solve beta naught, beta 1c and beta 1s from these three equations. But beta naught is given here directly. Okay? And that is a function of theta 1s as well as lambda, theta 1s, mu, theta naught. If you know these values, beta naught, from here you have to relate, because this is beta 1s, so you can get in terms of theta 1c and beta naught. That means you have to get this value, put it back here, then you can get beta 1s. Similarly, when you go here, you can get beta 1c. You take all the terms on that side, you get beta 1c. You have to solve this equation. This is for centrally hinged. Please understand. Now, let us look at two parts. One part is just this equation alone. Okay. Only that equation, assume that right hand side is 0. Okay. Assume. The stability of that equation. Okay. Stability in the sense, for a given initial condition. Okay. You give a small flap model. This is just a purely academic interest. Please understand. This is not for an actual grade. It doesn't happen like that. Academic interest. You have a differential equation. Now treat it, don't bother about it as a flap equation or anything. It is a differential equation which is given like this. You know the value of mu, which you can vary. Gamma is fixed. Lock number of a rotor blade, which is the aerodynamic by inertia. Typically that is in the range 5 to 8. Okay, lock number. 5 to 8. 5 is a little low. Okay. You get these values and then you give an initial input. That means the initial condition is you can have beta at 0, some beta 0 and beta dot at 0. Please understand, this is no longer a helicopter problem. I am not solving a helicopter problem. I am only looking at a differential equation of this form. Okay. So this is going to be, I will send you a homework which you have to solve. This is also part of your term. Same day I will give you. Okay. This is the equation. Depending on the value of mu. Okay. What will happen is mu is, suppose mu is 0. Assuming mu is 0, that means it is in hover. Okay. What is the condition? Your equation is beta double dot plus gamma over 8 plus, right? This is my flap equation in hover. Just no external load. Of course, gamma over 8 is the damping term. This is very similar to, you have your mx double dot cx dot plus kx equals f of t. I am taking it as 0. You divide by m, you will have x double dot plus c over m. You will write it at 2 zeta omega n x dot, right? plus k over m is omega n square x is 0. Omega n is the natural frequency of a spring. Here the natural frequency is 1. 1 means here it is a non-dimensional. Okay. So when the blade, if it is rotating, if you tap it, it will oscillate. The time for it to go up and down, one oscillation is exactly equal to the revolution time. Okay. So the rotor RPM is actually the flap frequency. Only in this case, please understand. That is why we call it 1 per rev. 1 per rev. 1 oscillation per revolution. Okay, that means if you tap it up, it will go down and then up, down. Then when it comes to 1 oscillation, blade would have gone through 1 revolution. Okay. Now you look at the damping part. So your omega n in flap, which I am going to call it rather than omega n, the notation I am going to use is omega bar. Bar is because it is non-dimensionalized with respect to omega. So you may call it omega Rf over capital omega is. This is the natural frequency of the blade in flap, non-dimensionalized with respect to, and Rf to denote that rotating flap. Please understand, Rf I am using the subscript only to denote rotating flap. If it is non-rotating, there is nothing, then it will just come down, that's all. Okay. So the centrifugal force actually gives the stiffening. And the natural frequency, non-dimensional, is basically 1. Then what about the damping? Gamma over 8 is exactly 2 zeta omega n. So you will have 2 zeta omega n is, and omega n is 1. So you will have 2 zeta is gamma over 8, or in other words, this will give you zeta is gamma by 16. That is that. What is zeta in the vibrating circuit? That is damping ratio. Okay. If you have gamma of the order of 0.8, sorry, not 0.8, 8. Gamma is 8. Gamma is of the order of 8, not 0.8, sorry. Gamma is of the order of 8. Zeta is 0.5. If gamma equals 8, zeta is 0.5. 0.5%. This is the damping ratio is 0.5. It's high damping. Very high damping. Okay. So basically the flap motion is heavily damped. And it takes very short time to reach its steady state. It is damped, it will take, later we will calculate how much time it takes if there is a disturbance, how much time it takes to reach its steady state value. Okay? That part will, from here we will analyze it later. So 0.5 flap motion is heavily damped. And the damping comes from gamma. Gamma is aerodynamics. Suppose if you rotate in vacuum, there is nothing because it is the rho. Density of air, lift curve slope. Okay? They contribute. Okay? Density drops, flap number drops. Now, this is a heavily damped system in hover. In the sense when nu is 0. But when nu is present, that means you have these terms. Forward flight. I cannot write like this because I don't have an equation where, oh, I take this. No, because my damping is a time varying damping. Stiffness is also time varying. You will find just for theoretical academic interest, for some values of mu, even if you give a disturbance, in this you know that if you give an initial condition it will damp out because you have a damping, it will decay. Whereas for value of mu beyond 1.3 or something, you will find that it will never damp out. You give a disturbance, it will keep on oscillating. But you don't go to that value of mu in helicopter plates, because helicopter plates operate below 0.4 maximum. Whereas that kind of a tendency comes with a high value of mu. So I will give you one problem which you are going to do numerically. This is a simple, this is an ordinary differential equation, only with time varying coefficients. Okay, how the solution will look like. Okay, for different values of mu, for given initial, I will send you with the assignment today. You analyze it, you plot it, you will find these are very interesting things. That's why in helicopter blade, if you want to analyze the stability, just for how the system will be stable or not, that part we will cover later. Right now, as a numerical problem, you can't write a solution like this. Draw numerically, get the solution, and then just plot it. Look at for different values of mu, how the solution really looks. For small values of mu, solution will converge immediately. Whereas when you give high values of mu, it will not, it will start oscillating, then it may start diverging also.
So what if we take sine beta instead of beta in the initial equations?
Which one?
When
Sine?
it starts?
No, that is see, then you have to take the full large amplitude equation. Okay? But we give small values of beta only. Even then it will oscillate. See, that is a nonlinear equation you are going. This is still a linear equation only. Linear equation with time varying coefficients. But why we don't take sine beta as it is? Because in most of the rotor blade analysis, beta is on the order of a couple of degrees, 2, 3, 4 degrees. Okay, maybe at the most 5 degrees. 5 degrees is what? 0.1 radian. Right? Sine beta is almost beta. So that is why that approximation is still valid. Okay, that is the reason. But this is as a academic exercise because you are getting exposed to a different kind of equation, which is normally not taught in regular math, because this is a time varying coefficient. But this will create problem later, not in flap, but if you have flap, lag, torsion, everything coupled, how will you analyze the stability of the system? That means you have to learn a new technique. So there is a Floquet-Lachlan theorem, then you have to do that. There is a transition, that part I will cover, which is fully math towards the end of the course, because that is just for your information. Okay? So right now you take flap equation with this just for exercise. Otherwise with all the right side, you put the whole thing, you will get this. We will discuss this part next class. Okay?